Okay, so in this video we're going to be looking at simple interest, a topic that is actually pretty relevant to the real world. So let's start off with a few definitions. Let's look at principal. Principal is the amount borrowed or invested. And then let's look at simple. Simple interest. And that, by definition, is the interest earned or paid only on that original sum of money that was invested or borrowed. So, let's write that. So yeah, simple interest is the interest earned or paid on the original principal. The interest itself, by definition, is the money earned from an investment, or if you borrow money, it's the cost of borrowing money. And then let's look at one final one. Amount. So amount is the total value of an investment or loan, where A is equal to the principal plus the interest. There you go. So this is B, this is A. Sorry. I. So now that you have the definitions, we can actually look at a quick example. Let's say you have someone who invests $3,240 at 2.4 simple interest. So, let's say this is per annum. Like this is shorthand. If you write 5% per A, that means per annum, which is another word for so that's just one thing you gotta put there. So let's calculate 3240 after the first year. How much interest? So the interest is going to be 2.4%. So we're going to multiply 0.00. Sorry. The interest is 0.024 times 3240. And that gives us $77.76. because 100% is 1.0. That's 100%. That means 99% is 0.99, which means 1% is 0.01, and 2% is 0.02, 2.4 is 0.024. So if you see this, don't be confused. When you multiply something by this, or if you want to multiply something by, if you want 75% of something, you can just multiply like the number, like say 10. I want 75% of 10, just multiply by 0.75, and you're left with 7.5. Same with hey, if I take 25% away of 10, you can just multiply by 0.75 because you're left with 75%. So yeah, moving on, let's continue that same problem. 240 at 2.4%. Let's calculate the number, let's calculate amount and total interest after 20 years. And that's very easy to do. You could actually do it the hard way, 0, 0, 32, 40. This is the year, this is the interest, this is the amount. 1, 2, 3, 4, I get every year 77.76, 77.76, 77.7. And you just keep adding that to that. You get you'll get 33.17.76. Next one, 33.95.52. You could do it like that. Or you could come up with a formula, which is 77.76 times t plus 32, 40. And if you plug in 20 for t, then you get 47.95.20. So this is the total that you're going to have after 20 years. That's the amount. The interest is actually this, which is 1555.20. Another thing we can calculate here is that's the gist of the interest here. Let's do another one. Another example, maybe something a bit more complex, so we can actually challenge ourselves. Let's look at someone who invests 48.50 at 7.6% per annum. That's simple. Interest. Now, let's say she wants her money to grow to 8,000. How long does she have interest rate, 7.6%, or actually 0.076. We have our amount that we want to calculate. So usually we have A equals principal plus interest. So let's put this into our formula. Well, in this case, our simple interest is going to be A equals B plus. Our interest in this case is going to be the principal amount times the interest rate times the length. Now we can solve for, t. So A is equal to 8,000 is equal to 4850 plus 4850 times 0.076 times t. And if we were to calculate this, we'll simplify that, I'll bring that one over to that side. That's going to be 3150 is equal to 0.076 times 4850. That'll give me 368.6 t. If I divide, I should get t equals 8.546. So since t is in years, so yeah, about 8.5 years. If you want to be exact, you can actually take the 8 away and say that's 8 years and 0.546 and multiply that by 365. You get 119.2. That gives me days, so 8 years and 119.2 days. 0.2 is a fifth of a day, so 24 over 5. Yeah. I'm not gonna calculate that. Just being extra at that point. But yeah, that's what simple interest is. The interest that you incur or get or pay is the same amount, the original amount on the principal. So I hope you liked that video, this topic. The next one we're going to be looking at compound interest, also known as future value. So tune in for that one. But as for this one, that's all for this video. I shall see you in the next one. Okay, so in this one we're going to be looking at compound interest, or as it's also referred to, future value. So what is compound interest? And unlike simple interest, which is just interest calculated on the principal amount, and that's what is kept the entire time, compound interest is interest that is added to the principal before the new interest is calculated again. So say you have like a savings account with like $2,000 in it, and it pays like, say, 10%, which is imaginary because you never get that. 10% of 2,000, after the first year you'll get 2,200, and then again the 10% is not 200 again. That would be simple interest, but in this case you get another 220 because you get 10% of this value, the new value. So that would give you another 220. So you get 2, 4, terms of a loan. So another thing we gotta learn is compounding period. And this just refers to the interval at which the interest is calculated. So annually means, if you have annually, which is yearly, one time per year. You have semi-annually, which is twice per year. You have quarterly, which is 4 times per year, and then you have monthly, which is 12 times per year. You can also have bi-weekly, which is 26 times per year, or weekly, which is 52 times per year. But this stuff is stuff you already know. So let's actually just jump right into an example. Let's say in this case you have somebody who borrows money. That's usually where compounding comes in. Simple is when you are making the money, when you borrow the money and you have to pay it back. Banks usually like to do compounding interest, especially government loans or like student loans. So yeah, $5,300, and you borrow at 4.6%. Let's say annually. So let's check to see how much he has to pay back this guy if he borrows his money for 10 years. So we're gonna be calculating in 10 years in the future. Calculating the future. Oh, I wrote it there, but yeah. Which is actually the letter A. In the future. So let's start calculating our 4.6% compounded every year. So if we were to do the math, after 1 year, that's our interest rate R, and this is 1. After 1 year, you would have to owe back 5543.8. And if you do the same calculation again, now with this new principle, now we do the same formula, but now this is our new P. So we do 5543.80 1 plus 0.0. You get 5798.81. And if you do it again, now with this as our principal, 5798.81, 1 plus 0.046 times 1, you get 6,065.56. So clearly, the one thing that we're doing again and again to this number multiply this a certain amount of times, right? Which actually is t. So, in our case, I could actually just put in my initial 5300 and multiply that by 10 times by this bracket, which is this number, to the power of 10. 10 times. And guess what? That'll give me the exact number I'm looking for. 8309.84. After 10 years on this loan, you would have to pay that much back. How about we look at the same one? Let's see. Actually, let's look at a new one. Let's look at an investment at this one. On this example, let's look at a $5,000 invested. We're going to invest at 4.8% compounded quarterly. So let's say that we have some parents who invest $5,000 into an account that pays 4.8% and is compounded quarterly. So at birth, this is now we want to find out the amount that this will grow to at 21 years old exactly. So, one of the first things we gotta do is well, I forgot to write this properly. This is actually invested at 4.8% per year, but it is compounded quarterly. So this 4.8% is actually for the whole year, but the compounding that happens quarterly, we actually have to divide by 4 because that means 4 times a year. So 4.8% over 4 is 1.2% per quarter. So every quarter it's going to compound the interest by 1.2%. And over the year that would be 4.8%, but let's plug this into our formula. But first we need to find the term in terms of how many quarters. How many times we're going to multiply this into our principal for 21 years. 21 years equal to how many quarter years? Well, that's simple. We just multiply that by 4, which should give us 84. So we have 84 compounds at 1.2%. So let's write this down. Now this and run with it, and make sure you get your best bang for buck when you're calculating your future value. So yeah, that is all for this video, and I shall see you in the next one. Okay, so in this video, we're going to piggyback off our last video of compound interest, which we already went over what compound interest is and how compounding periods work and whatnot. But in that video, we did future value, in which we calculate how much a current investment or loan will cost or earn in the future after a certain point. In this video, we're going to look at present value, which is basically us calculating the principal we would have to invest now to get a certain amount, or to get a certain future value in a certain amount of time. So, in this case, let's work into it. So, let's look at an example of a investment that we want to make to grow to our target is $15,000, and we want to invest this at 6% annually 6% interest per year, compounded. So, how much money should we invest today? What is our principal? So, now let's actually do our calculation. So we know that our interest formula is that our amount will equal our principal amount times 1 plus the interest rate over the number of periods that we're going to have, or compound periods. So we know that, let's see. Oh wait, one thing that I left out of the word problem is that we want to hit our 15,000 target at 6%, but we want all this to grow to 15,000 in 10 years. So how much should our principal be? So we know our amount is 15,000. Our principal, we don't know. We know that our interest rate is 0.06. And we know that we want to do this in 10 compound years. So it was actually that simple all along. Just rearrange and you have and if you punch that into a calculator, there you go. If you invest $83.75 today and you make 6% interest compounded annually in 10 years, you'll have $15,000. That's kind of what people say to do with the stock market. Invest your money into the S&P 500 index, which has a historical value of 6%. Or was it 10? I can't remember. But yeah, 10 years. That's basically the number you're going to be looking at. lucky tree. So let's write out our formula. And now we can actually start solving this. Let's plug in our initial values. Should have 50,000. That's I to the power of n. So if we rearrange this, or actually we can divide both sides by 5,000, and I should get, and this has to be actually not 40, I do have the time. So 10 is equal to 1 plus I to the power of 40. And now I can solve from here. So if we do some simple exponent math, I could just do root 40 to both sides. And get rid of that exponent there. And now I have 1 plus I. So this should give me roughly 1.0593 equals 1 plus I. And if I subtract 1 from both sides, I'm left with I is equal to 0.093. And this is the same as saying 5.93%. And there you have it. In 40 years, $5,000 today at 5.93. Compounded yearly will get you 50 grand. Which doesn't really seem like much. But yeah. So, I guess we could learn one more thing here. The rule of 72, maybe you heard of it, maybe you didn't. Basically, if you don't have a calculator, this is something like banks, investors, even regular people have used to basically approximate calculations involving compound interest. So basically, if you have an interest rate R% per annum, which is compounded, say, yearly, annually, then basically the rule of 72 means that it will take 72 divided by R to double your, basically to double in value. So say you have 8% as your R. If you do 72 divided by 8, it will take 9 years. 9 years for your, what do you call it? Your investment to double. And you can actually check it. If you plug those numbers in, say you put in a simple $1,000 and you put in 8% and you put 9 here. So this number here, after 9 years, your 8% variables, but it's a good thing to have. So, that is all for this video. I shall see you in the next one where we do annuities. That'll be fun. So yeah, see you on that one. Okay, so in this video we're going to be looking at annuities, specifically the future values. So what this means, or the word annuity, basically means it's a series of payments. Keyword, a series of, we really looked into series earlier, a series of payments or investments made at regular intervals. Simple annuity is an annuity in which the payments coincide with the compounding period or conversion period. So, in this case, we're going to be looking at simple annuities today. So, what this means is we're going to be looking at, how should I put it, payment plans and whatnot. Like regularly paid or regularly invested, and all of them will have interest compounded regularly on them, and we're going to try to calculate the future values on these payments. So let's jump right into one. Let's say we have somebody, or say me, say I want to invest $1,000 at the end of every 6-month period. And let's say that the annuity on this investment is going to earn me 4.8% per annum, which is annually, but it is compounded semi-annually for 20 years. Now, I want to find out what the future value here. So let's calculate the interest rate first, because per year it is 4.8%, but compounding semi-annually, I am looking at, instead of 4.8, I'm looking at 2.4% or 0.024. And another thing we have to fix here now are 20 years period, because we're compounding twice a year. I'm going to have 40 compound periods. So now if we actually plug this into our series formula, if you remember I think it was our geometric series, R-1. So looking at this is because when you look at this payment plan every 6 months, so if you start off with 1,000, the next for the first time you start off, let me reword this. You start off with 1,000, then the first compounding interest that happens, you multiply by 1.024. And then the next time you do it, the third term is going to be whatever this value is multiplied by this again. And then again, and again, and again, and again, until like you get to so that's one. Until you get to here. And then that, once you add all these up, then you get the sum at 40. So that is why we're looking at a geometric series here. So instead of like writing all this out, we're going to use the formula we learned. So we're going to plug in our initial, our first value, A, 1,000. And then we have in here the bracket, we have our interest rate that's being multiplied again and again, 1.024 to the power of how many intervals? 40 minus 1. 1.024 is our R. So if you punch this into a calculator, you actually get 65,927.08. And there you go. If every 6 months you put in $1,000 into an account that is earning 4.8% interest per year, compounding it semi-annually for 20 years, you can actually save up 67,927. Enough to save up for a used Porsche. Well, let's look at one more example. Let's say we have somebody who puts away or $500 every 3 months into an investment, the annuity at 5.2% per annum. Compounded quarterly. How much will her future value be after 25? So, again, let's start calculating the interest rate per quarter. 5.2% is per year. Per quarter, her interest rate is going to be 5.2 divided by 4, 1.3. 0.013. And the term is actually going to be every 3 months. Quarterly. right to the beautiful chase. Where we have $500 and our interest rate at 1.013. Yep, that looks about right. And now we have $101,487.91. That is us compounding. Really makes you want to save. Let's look at one more. Let's say I want to make monthly deposits into an account. I don't know what my investment is. Let's call it X. And let's say this annuity, this account, gives me 9.6% per annum, compounded monthly. But in the future, I want to have $500,000 at the end of so how much do I need in my investment? So I could write out my geometric series, which is first, I gotta figure out this 9.6% per year monthly should give me 96 divided by 12 is 8. Yeah. Well, 0.08, 9.6 over 12 will give me 0.8. So my I should be 0.008. So that's my R value, 1.008. I have my sum value as 500K. And I should be able to solve this by putting in, I don't know what my A value is, but I do know what my interest rate is to the power, well, hold on, 30, I forgot to calculate my N, 30 years times 12, that should give me 360. So, if I calculate this correctly, I should be able to get well, I'll punch this over there. I'll just cross multiply. A is equal to A value to be $240,000.80. There you go. $240.80, not 240,000. Can't believe I said that. Okay, put in $240,000 into an account every month and you'll have $500K at the end of 30 years. That makes more sense. So yeah, that's all for the video on future values. Tune in next time for present values, annuities. And yeah, that's all for this video. I shall see you in the next one. Okay, so in this video we're going to be looking at annuities, but in terms of present values. So in the last one we did future values, but in this one we're going to be looking at present values, which means what do we need now, or how much we need to invest now, or yeah, mainly invest. So let's look at say something that is 8.3% per annum compounded annually. The question is, how much do I need to invest today to provide $500 per year for the next 10 years? That is the question at hand. So let's start looking at how we could provide this, so I don't have to do any extra calculations here. Compounded annually, so my interest rate is per year. I got I equals 0.083 and equals 10. So you can just pull up the A is equal to, just say PV, present value, times 1 plus I to the power of n. So present value is equal to A over 1 plus I to the power of n. So let's look at this. Say, if you look at the end of the first year, say PV is equal to $500 over 1.083 to the power of 1. That is PV1 end of first year. And then PV2 is 500 over 1.083 to the power of 2. And if you continue that pattern, PV10 will be 500 over 1.083 to the power of 10. The reason why it's still 500 is because I want 500 per year. That's our target. So, if you look at the way I went about this, then you can see that I'm basically gearing up to add all these together, which again gives me my geometric series. So let's just skip right into the good stuff and just use our geometric series. I was going to kind of like sneak my way into the geometric series, but I guess you saw right through that. So I got in terms of my interest rate here that I'm using in my series, my series isn't really growing. So, unlike before, where I had the interest rate being multiplied by my amount or my present value, my interest rate is actually being divided by my interest rate, so that'll give me, so if I was to write PV1 out, it would actually be 500 times 1.083 negative 1. And then the next term would be 500 1.08 negative 2 negative 3 and so forth. So my geometric value is not actually going to be a full positive amount, so my first value is this one. So that's my A value, which is 500 times 1.083 to the negative 1. And then I have my R, my interest rate, which is this. To the power of n, which is 10 years, minus 1. All that divided by 1.083 negative 1 minus 1. A little bit more complicated than I like it to be, but let's punch that into a calculator and you get 3310.11. So I would need to invest a sum of $3,300 and, well, 3310.11. I would need to invest that now to provide a payment of $500 every year for the next 10 years. Well, that's interesting. Let's try looking at another example. Something a little bit more lavish. Let's see. Let's look at the exact opposite of an investment. Let's say a loan. Let's look at a loan from a bank. Let's say the loan was for $200,000. $200,000 loan. And let's say the bank charges 6.6% per annum. Compounded monthly. And let's say we're gonna take 20 years to pay this loan off. So let's say I want to take this information and find out how much I'll be paying monthly. So let's start off with the interest rate compounding monthly. So 6.6 over 12 should give me 0.0055, and my end value 20 times 12, that should give me 240 trigonometric series. Let's just write that out first, and I'll start plugging them in. So, now that I have all this information calculated, I have my N and my I. I'm going to start substituting. Oh, I don't think I explained this formula. This formula, there's a long derivation for it, but this is the formula for present value of an annuity. So let's start plugging in. Well, like R is up. The letter R represents the monthly payments I'm going to have to do. N is the number of payments. The number of payments. I being the interest rate, and V being the present value of the loan. In our case here. So if you were to write this out, we have R, which we're trying to find out. And then in here we have 1 minus 1 plus 0.0055 to the power of negative 240 over 0.0055. And this will all equal, we have 200k equals R times 133.072. And when you divide both sides by 133, you actually get R is equal to 1502.94. That will be the monthly payment to pay this off. And that is a hefty loan because the monthly compounding, that's what's really screwing this person up. This person being me in this completely imaginary case, but yeah, that is all for this video on present values and annuities. I might actually do a video on deriving these formulas for present value and future value annuities and even compounding interest. I feel like that's a really nice and confusing video to confuse people with. So that is all for this video, and I shall see you in the next one.